Alright, so let's see an example of a quantum coin flipping protocol. It's not going to be the best coin flipping protocol that we know, but it's definitely going to be better than any classical protocol for coin flipping. So here's how the protocol works. It's going to depend on a family of 4 states that I wrote over here, phi bx, where b is a bit, x is also a bit. They have the property that if you fix b but you change x, the states are orthogonal, but then for different b and the same x, they're not orthogonal. This is going to be important for the protocol. So how does the protocol work? At the first step, Alice chooses a random bit x in 0, 1 and a random bit b in 1, 2, and she sends the state phi bx over to Bob. Bob receives the state and he puts it aside. He chooses another random bit b prime in 1, 2 and sends b prime over to Alice. And then finally, in the last step, Alice reveals her choice of x and b to Bob. What Bob does is that he checks that the state he received in the first stage from Alice is indeed the state phi bx. Right? So this is a state over a qubit. Once he knows what the state is supposed to be, he can create an arbitrary basis that contains phi bx as one of the vectors and then make a measurement in that basis, check that he obtains the outcome associated with phi bx. And if this is the case, then both of them output as their coin flip the parity of b and b prime. Where note that here with my notation, b and b prime are either 1 or 2, so what I mean is that you just add them modulo 2. And that's the bit that you use. Okay, so does this protocol work? Well, first, observe that it is correct. If Alice and Bob are both honest, then we do get a uniformly random bit flip. That's just because b and b prime are both chosen uniformly at random. So this is okay. Now, in terms of security, the protocol is not going to be correct. What you can show is that this is a strong coin flipping protocol with bias a quarter. As I mentioned in the previous video, the best that we can achieve is bias about 0.21. So this doesn't quite get us there, 0.25, but it's not that bad either. So we have to argue this. Security against cheating Bob is easier to argue. So let's look at it. Because what can Bob do? Well, he can influence the outcome of the coin flip in as much as he can make his choice of b prime depend on b. So the question is, how much information do the states phi bx leak about b? And in order to answer this question, we need to look at the reduced density matrices. And what you can check is that the reduced density matrix, if Alice is honest, on Bob's side, when b is equal to 1, this will be the matrix, it's a matrix over a trit, a half, 0, and when b is a 2, it will be the matrix a half, 0, a half. And you can compute the trace distance between these two matrices, and this tells you that the probability with which cheating Bob can influence the final outcome is at most 3/4. So we get bias a quarter from the point of view of cheating Bob. So that's good. Now, cheating Alice, I'm not going to do the analysis because it's a little bit harder, but you can also show that her maximum probability of biasing the outcome towards 0 or 1 is a quarter. Here's the question is, whenever she sends phi bx over, can she later decide on a different bit b that she had encoded as a function of b prime that she receives from Bob? In fact, for all we know, she doesn't even have to send one of the states phi bx to start with. She could prepare, again, some complicated entangled superposition with some system that she's keeping to herself, maybe measure that system depending on b prime, and then depending on that, convince Bob that her b was something different than what it was originally. So it becomes a bit messy, the analysis, but it's not too hard to do, and you can argue that Alice's bias is at most a quarter. And if you think about this protocol, it's very similar to the idea for a coin flipping protocol based on a perfect bit commitment protocol that we discussed in the previous video. This is really what these states phi bx are doing for Alice. They act as a commitment of the bit b without revealing too much information. But we don't have perfect commitments, so we have some kind of a weak commitment where Bob can gain a little bit of information but not full, and Alice can change her mind a little bit later in the protocol but not completely, and this is what gives us this bias a quarter weak coin flipping protocol.